He was with DSP Microelectronics Group, Broadcom Corporation, California, where he designed analog and digital integrated circuits for signal processing application. From December 2008 to February 2010, he was with Max Linear Incorporation, California, where he was involved in designing integrated circuits for CMOS TV tuners. From March 2010 to November 2010, he was a postdoctoral researcher with University of California, Los Angeles. From December 2010 to December 2011, he was an assistant professor for Department of Electrical and Electronics Engineering, IIT Kharagpur. From January 2012 to May 2017, he was an associate professor with Department of Electronics and Communication Engineering, Amrita University. Since August 2017, he has been the associate professor at IIT Kharagpur. With his research interests include analog and mixed signals circuit design, data converters, and signal processing. He received the 2008 Analog Devices Outstanding Student Designer Award and the co-recipient of 2013 CICC Best Paper Award. I would like to request Dr. Bibhu Datta Sahoo to come on the dais and deliver his talk on challenges in data converter design in nanometer CMOS.
Thank you for the introduction. I should use this one, right? Not this. Anything. Okay. Sorry, I didn't know that I had to put this, hook this up. I thought that we can go through that one. Oh, you gave the slides. That's one. Okay. So my apologies for this, and thank you for the introduction. Now, I changed the topic, title of the topic a little bit from what is there right now in the brochure. I changed it to data converters, applications, overview, and design challenges. So I realized that there are a few second year, third year, and final year students over here. So I'll gradually introduce what is a data converter by first going through the applications and then go into some different types of overview of different types of data converters. Okay. And then get into some design challenges. Now, the reason I chose this progression of the talk is because in ADC design, in data converter design, a person has not only to be good in circuits, but also in signal processing. And I mean, you should also be a little bit, you should know a little bit of math also, because there is a lot of random processes, probability random processes also that come in when you're really trying to build modern generation of data converters. That is the data converters that are used in your cell phones at this point of time use a heavy amount of signal processing and math in it to make sure that your data converters give you the right performance that you are supposed to get. Now the motivation for the talk is, if you see, you are sitting around a lot of tons of data converters around you right now. At this point in this room, everyone has a cell phone. We are going through this projector, which is a DAC right now. The signal is sent digitally from the computer onto that one. That is converting the digital signal back into analog and projecting over here, which is an analog signal. So human beings perceive analog signals, okay? The world behaves in an analog manner, okay? But processing, human beings are comfortable processing stuff in digital manner. So, and that is where we have this data converters, which converts an analog data into a digital and vice versa. Now, where do they come? So analog, everything is analog in the world. We need to sense, sample, and then control something. Classic example of controlling is your aeroplane. You will be seeing the wings changing, the RPM of the engine changing. Similarly, your car also. When you're driving a car, it's full of data converters, okay? I recently learned that the modern day automobiles, 40% of the weight of the automobiles comes from the wire harness. Because all the electronic wires, this is what the TI people told me, that 40% of the weight of the car actually is wire harness. Means there are so many wires going back and forth. So it's full of electronics. So you sample the signal, you sample a lot of stuff in the car, then you control something, lot more stuff in there. So it's a sensor, actuator. Sensors sense your signal, then you digitize it, you do some processing, then you send the process signal and control the actuator. Okay, so analog media and transducers. So you take the signal. Now before the signal gets into any kind of into the digital domain, you need to go through something called a signal conditioning circuit, because the quality of the signal might not be good. Okay, so there is a signal conditioning circuit followed by a to D, which is converting the signal from analog back to A to D, means analog to digital. Then you go through some digital processing. Then the process signal then goes to a digital to analog converter, which converts it back into analog. Then it goes to some kind of a driver circuit or conditioning circuit, and then controls the actuators. So that is the overall. So any system in the world right now will have this kind of a interface. Now what is the reason we? Okay. What is the reason we go for this? So digital signal processing is much more sophisticated in the sense that it is less immune to noise. Okay. So there is if you look at an AM radio, if you listen to the old-fashioned radio, you hear some kind of humming noise or something. But if you listen to a digital TV or digital radio, you will see that the noise and everything is gone. Okay. So it is less sensitive to analog noise. You can do a lot more functionality. So I'll show you some of the latest generation, what people have done. A lot more functionality can be embedded into a small module. You guys have gone through so much of workshop on digital automation and testing. Probably today morning, there was some session where you went through some digital place and route. So digital tools are way advanced. Okay, they are so advanced and they're so sophisticated. You can automate a lot of design and testing. So the goal is that we should keep that means the digital circuits can be, since we are human beings, we are trying to design some stuff, we want to make sure that it works, right? How do we make sure? Nature is going to we are trying to understand the nature, so we should make sure it works. So that means we have to apply all kinds of vectors, we have to figure out techniques to make sure it properly works. And in the digital domain, there has been a lot of advances which have enabled this automated design and testing. So if we convert a signal back into analog and do a lot of processing in digital, we can make sure that the system works in the first go almost, I would say 90 to 95% of the time. Now, digital circuits, you know that the technology has been scaling. I'll show you a nice graph over 100 years, how transistors have scaled, how things have scaled over the last 100 years. I'll show that later on. So because of the scaling, you can embed a ton of functionality in a very, very small form factor. Okay. And that's so digital circuits benefit from that scaling trend significantly. So that's why we should go into digital domain, do all kinds of processing in digital domain. Now we can also do a lot of high precision arithmetic in a digital domain. Now, right now you have 64-bit processors, and also you can do arbitrary precision also manipulation. And with 64-bit processors, you can go for even higher bit precision math operation using some software techniques on top of the in the processor. Now, however, data converters are difficult to design. So these are all the benefits of digital signal processing. But to get to the digital domain, we have to have data converters. Now, data converters are difficult to design due to ever-increasing performance requirements. So I'll go through this. So let's try to understand what is the meaning of ever-increasing performance requirements. We had 2G, 3G, 4G, 5G. We want, as soon as we start downloading, it should download immediately, right? So where does the downloading thing come from? The circuits have to be fast. And as you know, what is coming through the air, so all the bits are coming through the air. It's analog signal, right? So the RF receiver has to receive it, okay? So now from that receiver, we have to digitize the receiver and figure out what are the bits that are coming. And then, so that means we have to operate. That means if I want a huge data rate, I need to have a larger bandwidth of the thing, bandwidth of the system. If I need more bandwidth, I need bigger and bigger sample rate. Why do we need higher and higher sample rate? All of you have studied Nyquist criteria, right? In signal processing, to avoid aliasing, if I have a larger bandwidth, I have to sample the signal at a faster and faster rate, right? So if I have to sample at a faster rate, so it becomes difficult to build circuits. As speed increases, it becomes more and more difficult to. So now, right now, all of you know the need for ever increasing performance requirement. We really need more and more performance every day. Okay. Now, these data converters present a performance bottleneck in a lot of systems. And when we say bottleneck, what it means is that we as engineers, we cannot get everything. There is no free lunch in the world. Okay. So there is always, we engineers have to deal with something called trade-offs. And especially in analog design, there are a lot of trade-offs that you have to go through. And in case of data converters, the trade-offs that come in is speed, resolution, and power dissipation. Means if I want a higher sample rate, I have to burn more power. If I want more resolution, I have to burn more power, right? So now we have to now make a choice. Should I go for large number of bits, or should I go for larger speed? Okay. So now we can trade off speed versus resolution. So I'll give you an example how we trade off speed versus resolution. We'll work out a simple technique on the board where we'll figure out that if I sacrifice the resolution, okay, if I sacrifice the speed, I can get arbitrary resolution. Okay, I can get larger and larger resolution if I can reduce the speed. So we have to. So these data converters present performance bottlenecks in terms of speed, resolution, and power. Okay, and these tend to overall limit the performance of a system. So I'll give you some applications. Now these are some applications where the ADCs are used. So audio, TV, and video. Okay, how many of you have seen a Walkman? Right. So old days, right? Now Walkman, does it say a 1-bit ADC? Have you seen that? It says 1-bit ADC gives you 16-bit. Okay, all of you are using a headphone, right? What is the signal that goes into the headphone? Just a 1-bit signal, ones and zeros goes into the headphone. But you hear high quality signal, right? You hear very good quality signal in the ears, right? The headphone, all the cell phone transmits or any kind of thing that transmits is a 1-bit signal, okay? And the magic of signal processing comes in, and the magic of 1-bit signal, right? Our compromised resolution is really bad, but I can hear really good quality sound. How does it happen? I compromise on speed. So I do some kind of filtering and some other techniques, and I can get 16 to 24-bit resolution from a 1-bit signal. And almost all of the CD players in the world use that technique. You can go and open up any CD player, it will say 1-bit ADC. Okay? And your headphone is a 1-bit. And if you see, okay, USB is not a right example, but that's how, so digital cameras are there. You use ADCs in there. You have to digitize the signal, right? Automotive control. Almost all the automobile, all the cars and everything are fully automated nowadays, okay? So the engine, everything, the RPM, so there are shut-off mechanisms and everything. So these are automated. Appliances, right? Microwave shuts off automatically, sets the power, okay? Toys also have now ADCs. So you have these flying, what do you call those? Drones. So they have a bunch of ADCs, okay? In communications, mobile phones, wireless transceivers, routers and modems, tons of ADCs sitting right there. Computing applications, storage media, sound cards, data acquisition cards. So all of you must have done some embedded systems courses in your undergraduate program. So you would have used data acquisition cards to acquire some signals using NI, DAC cards or something. They have ADCs in there. Hard disk, okay? Keep in mind a hard disk, we say that it's a digital media, but the signal that comes out from the head, this is the head of a hard disk, is purely an analog signal. You do have heavy amount of analog signal processing followed by digitization to really get back the signal, okay? Instrumentation, oscilloscopes, fancy oscilloscopes that you see have tons of ADCs inside that. Scientific equipment, MRI, CAT scan, all these machines, all the bio equipment, medical equipment, they all have data converters built into the system. So these are some of the applications that I could think of. So I would categorize them as consumer electronics, communications, computing, and instrumentation. Now, this is another application that is coming up, okay? It's a pure defense application, and it's called phased array radars, okay? They use the concept of beamforming. The phased array is a very old concept, 1940s, 50s concept. but they were not able to implement it. How many of you have used modems or routers at home which has two antennas? Two antennas. That is called beamforming. Multiple antennas, it's a multi-input, multi-output system, MIMO. So this is now what they do is they will use, I got recently the requirement, they use like 3000 ADCs inside a system in a digital beamformer. 3000 ADCs. Actually, they go for a full wafer digital beamformer. 18-inch wafer is fully used for digital beamforming. And so this is the overall architecture. This I got from Analog Devices application notes. So they'll have 3000 systems. So it's a fully, I cannot get into the details of this, but you can see that there is an ADC and a DAC sitting over here. Okay. So this is one of the latest applications where you have tons of ADCs and data DACs used in a system, and they burn close to kilowatts of power, because each one would be burning close to 1 watt. 3000 is right there, 3 kilowatts of power in one system. So imagine the amount of cooling that is required and all to make sure that the system works. I think this is one of the systems that has that. Now let's look into the space, how the data converters are used, application space. Now, as I said, the bandwidth is one criteria. The next thing is the resolution. Okay. The bandwidth defines the sample rate of the system, at how fast you are sampling the signal, and the resolution, how accurately are you digitizing the signal. Okay. So now, old days telephone, they used very low bandwidth because human voice is probably 10 kilohertz. So they go for like 100 to 200 kilohertz sample rate, very low power, this thing. Motor controls, like all DC motor controls in trains, cars, whatever, electric cars, they use audio uses very low sample rate, but very high resolution. Okay. But here we get 16-bit accurate system with just a 1-bit ADC. Okay. These are all for the DSL modems, which was called high speed over copper was DSL, then GSM transmitter, old days phone. Today's also phones use GSM. Digital TV, then HD displays, GSM base stations. Now kilowatts of power, as I said, goes into phased array radars and all. Also, some of the base stations burn close to kilowatts of power. If you go into the base stations, they will have a tons of signal processing in there, and they will be burning tons of power. Now, digital scopes. Okay. Nowadays, you get scopes that go up to 200 gigahertz of bandwidth. They can see sample signals of 200 gigahertz. They can acquire signals. Although they use optical techniques to sample the signal, but finally they convert it into electrical and display it on your screen. So digital oscilloscopes use very high sample rate, and wireline interfaces. This Ethernet cable that we are using, right? Now, the fiber optic cable that comes in, that also uses high bandwidth data converters. Okay. So these are some of the applications that I thought I should go over to motivate what is the purpose of ADCs and DACs. Now let me just quickly go through what is the history of how transistors have evolved. So how computing has evolved, actually, to be more precise. So there were mechanical computers in 1910. Okay. From mechanical computers, now this y-axis over here is the number of computations, and this is in powers of 10. So this is 1,000 times more. This scale is 1,000 times more, 1,000 times, 1,000 times. So we went from mechanical to electromechanical in 1930s, 40s, to vacuum tubes in 40s, 50s. And with vacuum tubes, we landed on the moon. Okay. That's how moon landing happened, with vacuum tubes, and barely the transistors, the BJTs had come in. And I would say I started my career in this phase, and you guys are starting your career over here. Okay. So you guys are starting your career when you are already, it's billions of computations you can do in a very small, in a second, billions of computations. So this is $1,000 buys these many computations. Okay. If you have $1,000, 60,000 rupees, an iPhone does this much amount of computation on you, on that. So imagine how the things have progressed. Now, the point I brought this up is the computations are proportional to digital computations. So what has happened is that the microprocessor industry has caught up with this, and they have gone up significantly. But what has happened is that the analog and RF design has not scaled as much. Okay, analog and RF design are way below. They're orders of magnitude 150x amount of scaling lower than what the digital amount of scaling has seen. And because as the technology scales, it becomes difficult to design analog circuits. And an analog to digital converter gives you a digital output, but it is doing analog processing on the signal. So it is very, very difficult to do analog processing. And some of the challenges that we have is, we have, as technology scales, the gain drops. Okay, so all of you have studied MOSFETs. The gain of a MOSFET is proportional to the R out of the transistor, right? What is R out? When the transistor behaves like a current source, it should behave like an ideal current source, right? It doesn't behave like an ideal current source. It has a certain finite slope. Because of that finite slope, the gain of the transistor drops. Okay, so and that the R out, drop in R out causes the drop in the gain, and that is called the intrinsic device gain. Okay, means if I take a single transistor, what is the GM times R out? GM times R out is the gain of a transistor, right? Is the overall gain of an amplifier. GM is a transconductance. A transistor does a trans voltage to current converter. Okay, you pass that voltage to current, the current that is produced onto a load R out, and if you pass it onto its own load, the R out, and you get the voltage swing, and that is called the device intrinsic device gain. So as technology is scaling, so I'm now talking about integrated circuits after CMOS has come. From CMOS onwards, as the technology has evolved, means we have got smaller and smaller transistors, right? Which is good for digital circuits. Circuits get faster, but analog circuits suffer. Okay, so the device gain drops. Okay, next thing that happens is that the nonlinearity of the device also becomes a problem. Now, I don't think I have the bandwidth to get into the reason for the nonlinearity degradation. Now, the next thing is, if I go from, as I scale the technology, right, I have to make sure my transistors do not break down. So I have to go for, I have to make, that means I have to scale down the voltage so that the field, electric field, doesn't arbitrarily becomes large and break down the transistor. Okay, so that's why we, as the voltage scales, the headroom reduces. Okay, headroom means the amount of signal swing that can happen will keep on reducing. Okay, so that's why we have to make sure that with that much amount of signal swing, we should be able to get the required performance that is needed. And that requires either you have to burn more power, or you have to do something, a speed versus resolution trade-off in there. Okay. Now, large variability and mismatches. Now, this is a little difficult to understand. Now, let me tell you, give a simple example. If I have a 10-storied building and I'm building it with bricks, I have a brick. Okay, that's a brick. Now, if I'm building a 10-storied building, the two 10-storied buildings are one brick apart. Will you notice the difference? You won't, right? Now, imagine you are building only 2 brick layers. You will see the difference, right? The amount of absolute amount of difference is the same, right? But the relative percentage difference is huge. If I have 1 brick versus 2 bricks, it's 100% different, right? If I have 1000 bricks over 1001 bricks, the percentage difference is less. Now that percentage difference, what happens is as transistor is scaling, right? The transistors are getting smaller and smaller. The amount of current carrying capacity, amount of GM that we get from a smaller transistor with respect to a bigger transistor in older technology. I mean, for the same GM, we'll need a much bigger transistor in the older technology. Now, if this smaller transistor varies by a small amount, the GM, percentage GM changes too much. And that would cause a variation in either the gain or something called an offset. And that would lead to different performance degradation. So that is called large variability and mismatches. So as technology scales, what you will see is that there will be huge amount of mismatches. Now, what do analog designers do to overcome the mismatch? I just gave an example, make things bigger, right? If the things are bigger, your mismatch is going to be reduced because the absolute value is the same, but the relative value is smaller, okay? And so that's why you have to make sure this becomes a challenge. But if you make things bigger, it becomes more, power becomes larger, area becomes larger. Bigger things are more likely to fail than smaller ones. So we want to make it smaller, but at the same time, make sure that we do not suffer from variability and mismatches. So that's why we come up with some signal processing techniques or some algorithms to overcome. We'll say, you know what, let the mismatches be there. I'll figure out some other way to overcome the mismatch. So that's where some pre-processing or post-processing comes in. Okay. Then survival in a system on chip environment. So this is one thing that is happening as technology is scaling. So what is happening is that, so let me go through 2 more slides and then I'll come back there to explain the survival in a system, survival in a SOC environment. So if you look at the 1983 phone, okay, this is the 1983 phone, which was in this era. All that phone had was discrete op-amp ICs, okay, discrete ADCs and DAC, 64 KB of storage. We don't even look at if something doesn't have 64 GB of storage nowadays. Okay, now imagine it was 64 KB in 1983. It had a bare minimum audio processor. It had a discrete frequency synthesizer because you need a clock to do something, right? So that's a frequency synthesizer, a discrete demod, and a simple 16/32-bit microprocessor, and it was this big. It was called a brick phone. In those days, it was called a brick phone. Okay. Now let's contrast this with what you have now. This is 2015. I could get from Samsung website, Samsung Galaxy S8. 4G modem is there. Okay. Wi-Fi modem is built in. Bluetooth is there. GPS is there. Okay. 1 gigahertz microprocessor with 4 GB of RAM, 64 KB, and now a microprocessor has 4 GB of RAM. Okay. Now half dozen sensors, right? Fingerprint sensor, camera, front camera, back side dual camera sensors, gravity sensor. If it drops, it does some sensing. Half a dozen sensors, and 64 GB of storage, right? Now imagine all these they're all analog signals, and they are doing, the microprocessor is doing a lot of signal processing, and the modem is also doing a good amount of signal processing, right? I don't know why this is. Why is it not going? Okay. So now imagine this is the size of a chip which is doing the modem, which has an ADC and all. Now what happens is that that is now a system on chip. System on chip means you are building a full system inside a single chip. There is something called a system on chip. There's something called a system on package, SOP also, where they put 2 chips on top of each other and they have interconnections between them. So they do system on chip. Now in system on chip, you have a lot of analog signals, digital signals, a lot of activity happening. Okay. So when something is switching, something else is not switching. Now what happens is that when things are switching inside a system, right, they might affect the analog signal. Now let us try to take some simple number. Now if you happen to see your TV, okay, cable TV, or I don't know how many of you, if you see in the setup, there will be an option. It will say the sensitivity, the lowest amount of signal that it is receiving. It will receive close to minus 98 dBm of signal. Minus 98 dBm is probably a few microvolts of signal, right? Now that microvolt of signal has to be received and it has to display a picture, right? So that means your sensitivity, so that means your accuracy of the analog signal. We cannot, if it is let's say 64 microvolts, and if I put in some large switching happens, then that 64 microvolt becomes 256 microvolt, the bit flips. So you will have all kinds of problems when you are in a receiver or something. So when there is a lot of activity, digital signal processing happening, there is a lot of switching happening, and that affects the analog circuits. And as the analog voltage is reducing with nanometer technology, the amount of, we call this as crosstalk, means some activity coupling to another one, which is called a crosstalk, and that affects the quality or the fidelity of the signal that we are receiving. Okay, so just to give you a perspective, I just went over a few more slides. So now what people do is, it becomes challenging, that's why, because of these cases. Now you can use pure analog techniques, but they're area and power hungry and also time consuming. You cannot meet the production requirements. Okay, Now DSP techniques or signal processing techniques become more attractive as they use digital gates, and digital gates can scale with technology. So now let's see some of the bottlenecks also. Now in a communication receiver, especially in a cell phone, if I need a larger bandwidth, I need a larger ADC, high sample rate ADC. So it becomes a bottleneck over there. This is in a wireless receiver. So you can see an antenna. There is a mixer. This is an LNA, low noise amplifier. This is a mixer. So this is a super heterodyne, very 1930s, 40s concept. It's still being used. You mix it down to baseband. Okay. Then you have a filter, anti-alias filter, so that because you are sampling, you need an anti-alias filter to get rid of the aliases. Then you have an ADC, and then after you have digitized it, you go into digital baseband. You do a digital processing on it. Similarly, with a wireless receiver, you're receiving a signal over that Ethernet cable. What you receive is actually an analog signal. What you receive is an analog signal. Now that analog signal needs to be recovered. It's no more 1 or 0 because it's an analog signal. It will be some analog voltage. We have to now convert that into ones and zeros, and you do something called equalizer is there, which equalizes the loss in the channel, so it goes through a channel and it recovers the digital bits over there. Now another thing that happens is that when you turn on your phone, it takes some time to get the signal, right? It takes some time to get the signal from the reason it takes some time is that it has to figure out, it has to synchronize your clock, the cell phone clock, with the base station clock. And that's why nowadays nobody uses the hand, this thing, they all rely on the cell phone, because this gives you the accurate time. It synchronizes always with the base station. So there is something called a clock and data recovery circuit that comes in over there. And the CDR also are done with, now people do digital CDR using ADCs. These are the communication bottlenecks. It becomes a power bottleneck in a lot of biomedical applications. So yesterday you listened to the talk by Professor Sonkusule, where he mentioned that you need batteries, and if it's an implant, then you need to make sure that it has to be inside your body for 7 years without replacement, right? At a minimum of 7 years, because they cannot do surgery multiple times. So it becomes a power bottleneck if it's an EEG or ECG or an implant. So you would need some kind of signal. It is sensing something in your body, right? And it is then converting and giving some signals back. So you need data converters, and these have to be ultra low power. They have to run for years. Also, power bottleneck in IoT applications, wireless sensor node applications, and all. They become power bottlenecks. So I think I'll skip over this at this point. So this is the perspective how the cell phone has evolved over the years until 2014 is what I could gather from the internet. Now you can see the amount of functionality. It was 785 grams with 30 minutes of talk time, 8 hours of standby time. And now look at the current phones, 178 grams with 25 hours of talk time and 672 hours of standby time. Not to mention the amount of processing it can do besides. So that's the power of scaling that we have got. So now, as I said, so I'll give a brief overview of ADCs. So you have the analog world, and there is a digital world, and we do processing in digital world. And there is an interface ADC which converts from analog to digital, and vice versa, because you have to control something in the outside environment. You have to convert from digital back to analog. Okay. So real world signals are continuous in time and continuous in amplitude. Okay. Digital abstraction involves, you have to first make sure that when something is continuous, you have to sample it and convert it into discrete time. Okay. Then after you have converted it into discrete time, you convert it into discrete amplitude. And so there is a discrete, this is called a digital abstraction. Now the thing is, how to discretize in time and amplitude is A to D conversion. How to undiscretize in time and amplitude is called digital to analog conversion. Okay. So that means from discrete amplitudes, how do I get a continuous waveform? And that is a digital to analog conversion problem where you have to use something called a reconstruction filter. So I don't think I'll go into the math of these, but just to give you how it happens. So A to D conversion, analog signal, there is something called an anti-alias filter to overcome the aliases. Okay. Because of sampling operation, you end up with aliases. Okay. So then you do a sampling operation. You have to filter the signal, then you sample it, and then you do quantization. this sampling, then this sampling actually holds the signal, okay, which is discrete in time and also discrete in amplitude. Then you convert it into quantize, assign it to certain digital numbers, okay. D2A conversion takes in the digital input, converts it back into analog hold, followed by a reconstruction filter, which is nothing but a low pass filter typically, and gives you an analog out, which is a continuous time signal, okay. So the digital signal will be staircase kind of a structure, and the analog signal will be continuous signal. Now, we'll focus on ADCs for the remainder of this thing. So sampling is the first step. It's a 3-step process. Sampling, quantizing, and something called encoding, okay. People mostly go for uniform sampling, but you can also, if you are clever enough, you can go for non-uniform sampling also, okay. So non-uniform sampling needs special kind of signal processing techniques, so which is beyond the scope of undergraduate curriculum also. So mostly we focus on uniform sampling in the undergraduate level and also at the master's level. Probably at research you can go into non-uniform sampling because it's not mathematically a little bit complicated to get into the. Now sampling. Now analog design, people think transistors, this and that. Analog design is made of, I would say, 4 components: resistor, capacitor, inductor, and a current source, controlled current source. That's all it is, okay. We need to understand how to analyze RC circuits, okay. Every circuit on earth, no matter you open up the modem, it's a bunch of resistor, capacitor, inductor, controlled current sources. So that's all it is, okay. Now, and all you need to do is you need to know only one equation for a transistor. Let it be square law equation. That is good enough. All those transistors have deviated from square law because of scaling, because of velocity saturation. I don't know if you know this term already. Some of them, okay. So as technology scales, the electrons, the speed is limited, so you hit something called velocity saturation. So what happens is that your transistor is no more a square law. The MOSFET is no more a square law device. BJTs are exponential devices, bipolar junction transistors. MOSFETs are square law. The old MOSFETs were square law. New MOSFETs are no more. So, but you need to know only one equation, and as a designer, you have to play with that. That's all. Nothing more you need to know. RC circuit, how does an R and C work? Okay. Now, I'll give you a simple example. Okay, I'll give that later on. Now, a sampling circuit is nothing but a switch and a capacitor. And a switch is realized using MOSFETs, okay? MOS acting like a resistor. So this becomes an RC circuit. So what do you care about an RC circuit? What do you care about in an RC circuit? Time constant. Just the time constant, right? Now, as my sample rate increases, what should I do? My time constant of this network should keep on reducing, right? It has to keep on reducing because let's say I'm going at 10 gigasamples per second, which is 100 picoseconds. In 100 picoseconds, I have to acquire the signal. Now, an RC circuit, what is the basic thing? The rise time and fall time, it takes in one time constant, how much does it reach? 67% of the full scale. So to reach 99% of the full scale, how many time constants we need? 4 or 5 time constants, right? So we need roughly 7 time constants. Let's put some margin, okay? Designers, engineers always put on margins, okay? That is very, very important. Otherwise things won't work, okay? So you have to put in margins in every design. So let's go for 7 time constants. I won't go into the math, but there is exactly an equation which tells you how many time constants you need to sample a signal depending on the sample rate. Now this is an RC circuit, right? Simple RC circuit, switch resistance, and this capacitor. Now the thing is that when you're designing this sampling circuit, there are a few things that govern how should you size this capacitor, how should you size this resistor, and that will decide the quality of your data converter, because this is finally the input which is going to be digitized by your ADC. So now this R, I can manipulate the resistance of a transistor using what technique? What can I do? If I want to reduce the resistance, I will increase the width of the transistor, right? I'll keep on increasing and keep the length, channel length to minimum. So that means if I am going at a higher and higher sample rate, and if I keep this capacitor fixed at a particular value, though as a designer, I have only the width of the transistor to manipulate to get to the required sampling accuracy. Now, this sampling circuit, what happens? This is a sampling circuit. This is called a track and hold. Why is it a track and hold? Because when this is on, means the switch is closed, and the switch is closed, let's say during this much amount of time. During this much time, it tracks the signal. So you can see that it is tracking the signal. And remainder of the time when it is off, it is holding the signal. Then again, it turns on and it tracks the signal over here, and then it holds. So this is called a track and hold circuit. And this is discrete in, you are discretizing discrete time signal. So this signal that you get is called discrete time signal, not yet a digital signal. It is a discrete time signal, okay? So this is a discrete time signal. Now, when it is being held, okay, that is when you digitize it and convert it into a digital number, okay? Now, and then you can take it to a computer. So you take a sample, a signal, you convert it into discrete time, then you convert it into bits, into digital bits, and take it into a computer. Now, computer receives only the bits. It has no idea what is the thing in there. So if I give the signal, if I give digital bits to a computer after sampling a signal, in order to see what is the signal, what do I need to feed the computer, what additional information do I have to give? I have to give the sample rate also, because computer doesn't know anything else. It sees only bits. So now I have to give the sample rate and tell, oh, you know what? I sampled the signal at this rate. So now it knows, oh, that means the signal is within this much band. So then it can give you back the analog signal if required. Okay. So now after you have done the sampling, discrete time, then you go into quantization. Quantization means I have to convert it into bits. So now if I have to convert it into 3 bits, let us say my signal is going from 0 to 5 volts. So I have to now discretize that signal from 0 to 5 volts. That means if it is 3 bits, I'll have 8 levels. Okay. And those 8 levels, that means from 0 to 5 volts, I'll convert these into different. If it lies between this and this 0 to 0.625, it is 0, 0, 0, 0, 0. 6 to 1 to 1.25, it's 0, 0, 1. This is called sampling, mapping. This is converting the analog signal into digital. Now, as I said, there are 3 steps, right? Sampling, quantizing, and then encoding. So now here I have not shown the encoding, and I'll show the encoding as I go to the next, as we go on. Okay. So now sampling is a straightforward process. Sampling is a very straightforward process. There is nothing much into it, but it is not as straightforward as shown here. As you go into complicated circuits, high-speed sampling circuits are not as simple as this. There are much more to it than this, but this is a basic sampling circuit. Now, after the sampling, we'll talk about how the quantization happens and what is the encoding. Now, your strategy of quantizing a signal defines the type of a data converter. Okay, I have listed 4, but there are a lot more kinds of data converters also, ADCs. One is called a flash ADC. Okay. Now, see, anything that we say in engineering, it has a meaning. Flash. What is the meaning of flash? In a flash, right? So the camera flash comes in. It's a flash, right? It does. So flash ADC quantizes in a flash. Boom. A clock comes, quantizes. Clock comes, quantizes. It takes. So that's why it's called a flash ADC. Then something called a successive approximation register ADC. So what it does is, how many of you have done binary search algorithms in algorithms? How many of you know binary search algorithms? Okay. So what happens is that exact algorithm is coded in hardware and an ADC is realized, and that's called a successive approximation register ADC. It's as simple as that. So now the flash ADC, since it quantizes in a boom, it needs a lot more hardware. Then people thought, you know what, this hardware is too much. Okay. But it can go really, really fast. So the oscilloscopes that you see in your lab and anywhere, they all use flash ADCs. 90% of the oscilloscopes will use flash ADCs. Okay. So successive approximation registers are used at other places. Now, suppose now this flash ADC has a huge amount of hardware. Now I want to reduce the amount of hardware. So then they thought, you know what, I'll do something pipelined ADC. What is the meaning of pipelining? Pipelining is step by step. So what pipeline ADC does is takes a signal, quantizes it into low resolution, passes on something else to the next stage, and then this current stage receives the next signal, next sample, and keeps on quantizing in that fashion. Then something called a delta sigma ADC, which gives you very high resolution but very low sample rate. Almost all audio applications use delta sigma ADCs. Almost all audio applications. GSM receivers in the old days, the ADC in the GSM receiver in the old days cell phone had delta sigma ADCs. The GPS on your cell phone uses a delta sigma ADC because the GPS signal that comes from the satellite is way below noise floor. Okay. Now there is no way I can figure out the signal, what is the signal, unless I do get rid of the noise. And you know what, nature is very kind to us. It gives us noise, but at the same time, it tells us also the noise is zero mean. So nature is really kind. It gives us noise, troubles us, but it gives us noise in a manner that is zero mean. What does it mean? If I average it, it goes out. Okay. So you can try this experiment in your lab. Go look at the oscilloscope. Okay. Give a sine wave. And then you go into the averaging mode in an oscilloscope. Then you see a clean sine wave in there. So sine wave, if you see it without averaging, it is corrupted with noise. Without averaging, with averaging, the noise is filtered out. Okay. So the delta sigma ADC. So now let's look at what is a flash ADC. Now flash ADC works like this. So as I said, here I'll now switch on to the board a little bit. Let's say I have to digitize. I think I should use that side. I don't know whether they can see it. So suppose I have 0 to 1 volt scale. Okay. My signal goes from 0 to 1 volt and I need to digitize it into, let's say, 3 bits. So what do we do? We have, this is how I threshold the signals. Anything lying over here will be 0, 0, 0. Any signal lying over here will be 0, 0, 1. Like this, it will be 0, 1, 1. Now, who does this? So a bunch of comparators can come in. So I can build something called a comparator. Okay. And this comparator takes 2 inputs. It compares 2 signals. Okay. One of the inputs is going to be this voltage, which I generate using what? Resistor. I said analog design, we don't use anything other than resistor capacitor. RF design, inductor comes in. Okay. And of course, a transistor is there, which is a controlled current source. Okay. So there is a resistor. So these voltages are generated using, so this is 0.5 volts. And rest of the other voltages are there. So these go as an input to the comparator, and the other input is the input signal. Now, it's a flash ADC. It should quantize in a flash. So the clock comes in, triggers the comparator. Tell me whether it is greater than or less than the threshold. And what the comparator gives you. Suppose the signal is over here. How many comparators are there? C0, C1, C2, C3, C4. 7 comparators are there in a 3-bit system. So if it is an n-bit system, right, I would need 2 to the power of n minus 1 number of comparators. Okay. So if the signal is over here, what does the comparator give? This comparator will give me 1. This will give me 1. This will give me 1. Rest of all of them will give me 0. Right? This is not a binary number. Binary number should be 3 bits. Now this number has to be encoded. Okay. So that's where the encoding, I said that quantization has happened. Okay. Who does the sampling? The clock that comes and triggers the comparators does the sampling in a flash. Okay. Okay. And then gives the quantized value. This quantized value is then encoded and converted back into binary. Now keep in mind that this kind of quantization is called thermometer code. Why is it a thermometer? As the signal increases, the number of ones keeps on increasing, just like in a thermometer. The mercury keeps increasing if the temperature keeps rising. Okay. So similarly, as the voltage keeps increasing, just like the temperature increases, this number of ones will keep on increasing. So this is called a thermometer code. And this thermometer code is converted back into binary using a encode logic, which is called an encoding logic. So there will be a logic that follows. And typically that logic in a high-speed system, very high-speed system, is a ROM, read-only memory. So it's a ROM. Okay. A ROM. So these bits go and control the ROM and tells you, okay, this is the final output. Okay. It converts this into 0, 1, 1. This is 3, 0, 1, 1. Okay. So this is a flash ADC. That's what I have. So it's the simplest, fastest for high-speed applications. So that's why oscilloscopes are the highest speed application. Oscilloscopes use this encoding logic, And you know what? All of you can build this in your lab on a breadboard also. Just buy a bunch of resistors, high precision resistors. Resistors are cheap. Put them on the breadboard. Buy comparator. There are quad comparators and 8 comparators available. You can build a 3-bit ADC in your lab. And the comparator is clocked, clock it with something and put a flip-flop after it. You get the thermometer code. Take it to the computer, convert it into digital, and you have the digital A to D right there. So encoding logic takes thermometer code as input and gives binary output. Okay. So this is a flash ADC. Now, the problem of the flash ADC is that the number of comparators grows exponentially as the resolution keeps on increasing, right? Now, if the number of comparators keeps on increasing, the input is connected to all the comparators, right? Any system in the world, any wire has some capacitance, right? So as the input now sees more and more capacitance in the system. Now, the thing is that the bandwidth of this circuit, what is the bandwidth of an RC circuit? 1 by 3 dB bandwidth is 1 by 2 pi RC, right? So now, if I want to build a 12-bit system, I need 4095 comparators, right? Each comparator has some capacitance over here. Okay. Now the capacitance has increased, right? Now any system, for example, antennas have 75 ohms. TV antennas are 75 ohms. A lot of RF things are 50 ohms. So if your resistance is 50 ohms, right there your bandwidth is limited to 50 times 1 by 2 pi, 50 times the capacitance that you're seeing. So for high resolution ADCs, you do not use flash ADCs. Okay. So you have to go for something else. Now, how can you can I build a ADC using only one comparator? The answer is if I have a SAR ADC, successive approximation register. What it does is it does a binary search. Now, what it will do is, let us take the same example. So the input signal is over here. Okay. In a successive approximation register, it just has one comparator, some logic, and a DAC. Okay. So what happens is that it takes this input voltage, it compares first with the center point, mid value. It tells you if the comparator says it is 0, that means the signal is over here. Comparator gives you 0, the signal is over here. 1, signal is over here. Depends on which side, how the comparator is connected. And if it gives you 0, then the signal is over here. So now, first bit decision tells you whether the signal is in the top half or the bottom half. Okay. Then if the signal is in the bottom half, then it will compare with this value. Then it will tell you whether it is again this part or this part. So that's a binary search it does. And finally it gives you the quantization. So what it does is, that means in a SAR ADC, what happens is that every tick of the clock, you get 1 bit output. And this is the algorithm it follows. So it first gives you the MSB. If it is greater than this or less than this, the bit that I get is the MSB. Then I get the MSB minus 1. So if it's a 3-bit system, if the bits are these, this is the LSB of the system, which is the least significant bit. And this is the MSB of the system, which is the most significant bit. What happens is then in a successive approximation register, first I'll get this bit, whether this is 1 or 0. Then I'll get this bit, then I'll get this bit. Now what happens? Now the capacitance that the input sees is very, very small, right? But it takes n cycles to give you the output, because if it's an n-bit ADC, it takes n cycles. So it is slow, but it is used for like 8 to 12-bit resolution ADCs and for decent sample rate. One of the fastest, I think, ADCs, 56 gigasample per second, 8-bit ADC is the SAR ADC, which is, of course, time interleaved and all. So now after the SAR ADC, then people thought that, okay, this is taking too much time. That one is having too much capacitance. Can I do something better? So then they went for something called a 2-step architecture. This is the first step towards realizing a pipelined architecture. So what happens is that you have a sample and hold. Okay. What you do is you digitize few bits here. Then you convert this digitized value into an analog value. You subtract from the input and you have a fine ADC. So you have a coarse flash ADC and a fine flash ADC. You get the MSBs from here, you get the LSBs from here, and you combine them in a manner to get the higher resolution. So now the number of comparators reduce significantly. Okay, so I'll give you an example. So if I have an m-bit ADC, if you use a flash ADC, the number of comparators, as I say, is 2 to the power m minus 1. Okay, Now, if I go for a two-step architecture and each stage is resolving m by 2 bits, the number of comparators reduces. So for example, for a 10-bit ADC, I'll have 1023 comparators. And if I go for a coarse 5-bit and a fine 5-bit, you will have barely 62 comparators in the system. So the amount of hardware reduces. And the good thing about a two-stage architecture is that this is pipeline. When this is processing one sample of the signal, this stage, this is processing the next sample. So it is fully pipeline, and this is a two-step, I can extend this into multiple steps and get a true pipeline ADC. Okay, so now the next thing is, as I said, there is something called a sigma delta ADC. So I want to do that on the board. A sigma delta ADC is something which trades off with 1-bit ADC, you can get 16-bit resolution. So the way it works is, it takes in an input signal, it puts in something called, I'll write it in Z domain. This is an integrator in Z domain. So if you are not comfortable with DSP, so it's okay. So Z inverse divided by 1 minus Z inverse. Z inverse is in a DSP domain means 1 sample delay. Okay. So if I have this, okay, and I have a quantizer here, which is adding, of course, I did not get into that. So when I quantize a signal, I end up with something called a digital value and something called a quantization noise. Okay. So I can put in after the integrator, I can have a quantizer here. I can design a quantizer, define a quantizer like this, and the output of the quantizer comes and subtracts from here. So I can apply a V in here. Okay. Now this will be operating at a certain rate. Now this thing becomes something called a 2-input system. So if I this is a nonlinear system, by the way, because of the quantizer. The quantizer is a nonlinear system. So this becomes a 2-input system. So what are the 2 inputs? One is the input B in, and the other is something called a quantization noise. Okay. N means the sample. So if I say that V in of N is the sample index. So these are all sampled signal, let's say. So now what happens is this is a 2-input system. So this one is giving, let's say, 1-bit output. Okay. But I put a filter after this. I put a digital low pass filter and convert this into 16 bits. And that is what your CD does. And what is the low pass filter in your headphone? Is your headphone membrane. It acts as a low pass filter. It filters you and gives you a pretty good accurate signal. So now if I look at this, this is something you sample at a much higher rate. You are going at some rate here and you are going at some lower rate here. So you are trading off accuracy versus speed. So this is a delta sigma ADC. Okay. So I don't think I'll get into the details of this, but a delta sigma ADC actually gives you much more accuracy over a conventional ADC, but at the expense of the sample rate. Okay. The sample rate drops significantly. So again, going back to the nanometer ADC challenges, as I said, in nanometer design, we have, these are the different challenges which I've already talked about. So I just put this slide in the perspective to come back to this nanometer ADC challenges. But now, when you have, let's think of it. As I said, when I have issues in an ADC, right, that means my performance of the ADC drops. Okay. So now, for example, I have mismatches or something. Now, to give you a perspective of what is a mismatch. So keep in mind that when I built this flash ADC, when we realized this flash ADC, we had a bunch of resistors. And these resistors are defining the threshold voltages which are equally spaced, right? Now, how do we make sure that resistors are all equal? It's very difficult to make sure, right? I cannot find out whether they're equal or not. We try our best to make them equal, but they might not be equal at all. Okay. So now our goal is to figure out how do we estimate how much is this off from this? How much is this off from this? So that is called figuring out the parameters inside the system And once we know this is off from that, I get the digital bits. I can do some correction on this digital bits to get back the actual analogs, actual proper ADC output. Now, let me give you a simple example. Suppose I give you a black box and I tell you that the black box has a resistor and a capacitor. I don't tell you what is the value. I don't tell you what is R and what is C, and I tell you, can you find out what is R and C? Okay, so what will you do? And I give you an oscilloscope, and I give you one capacitor, and I give you one resistor, and I tell you, I give you one additional resistor and one additional capacitor. Okay, and I tell you the values of those resistors and capacitors because I'm giving it to you. You have inside this, what is there, you don't know. And that is exactly happens when I manufacture this. I don't know what is here, but I have to figure this out, right? Now let us say I have this system, R and a C. Now let us see how will you do it. To give you a simple example, I'll put a step input here. I can monitor the waveform here. What is the expression of the waveform if it is falling? E to the power minus t over tau. What is tau? R and C. So I get, if I look at the oscilloscope at any particular time, let's say t1, I will get V1 equal to e to the power minus t by RC. T1 by RC? Yes or no? Okay, so now we got that. That means ln of V1 equal to minus T by T1 by RC. Remember, I gave you one more capacitor, right? You plug in that capacitor over here. You know the value of this capacitor, right? So I apply same voltage step, I'll get V2. So I can do ln V2 equal to minus T1, same T1 by R times C plus C1. Done. I've solved for C1, right? So similarly, I can solve for R. I can plug in R in the next measurement between the input and output. And I can get the value of R. So I have two unknowns. I have to figure out the two unknowns. So what do I need? How many equations do I need? Two equations. So figuring out what is happening inside the circuit, figuring out the parameters of the circuit is what is called calibration or estimating this. It's a very simple technique. I gave, this is a very simple exercise. It is not as simple as this, the way I have shown it, because when I'm trying to estimate these parameters, remember I told you I gave you an accurate capacitor and the resistor and I told you the values. What if I don't have access to that? Can I do something else? Can I do some other fancy techniques, okay, to figure that out? So now, as I said, in nanometer CMOS, you have resistors that are not perfect. These are tiny resistors, right? And mismatches are large, so I have to estimate the mismatch between them. Similarly, these comparators are made of two transistors. They will have offset, they'll have mismatches. This will cause me some other error. So how do I estimate that? That estimation of the unknowns inside the circuit after the chip has come back is called calibration. And I will now go into something called so now when we are trying to estimate this thing, now I'll go into a little bit of math, okay? And we will use linear algebra, we'll use signal processing. And why linear algebra? As I said, we need two equations, two unknowns, just a linear algebra problem, right? So now let us say I have built a pipeline ADC. I haven't gone into the details of it, okay? Let me tell you in this manner. Suppose I have this part of a circuit, this is part of a pipeline ADC, one stage of the pipeline ADC, something wrong in this side, okay? Which is giving me very poor performance. I have to fix this circuit, but I don't have access to this. This is inside the chip. I have no access to this circuit. All I have access to is this input, okay? And these outputs, digital outputs and this digital output. How do I figure out what is wrong here? Okay. Now I know what is the transfer function from input to output. So it is given by two variables, alpha and beta. I have no idea what they are. Okay. Now I can cleverly apply certain sets of inputs. I won't get into the details of that, and set up a system of equations. Okay. And with those system of equations, I can figure out these parameters. Now these are in this system, if it is a 3-bit system over here, I'll have 7 such parameters here and 1 such parameters, 8 parameters. So I need 8 equations. So how do I set up those 8 equations? This becomes what is called, this is one of the challenges, because in the nanometer CMOS, this part of the circuit is messed up. It's not great. So I have to fix this circuit. But I don't have access to this circuit. As soon as I put access to it, that means my performance speed of the circuit drops. Because if I'm bringing it to the pad, performance drops. So I cannot bring it outside also. So I have to make sure that I can figure out the performance by looking at only the inputs and outputs. I have access to nothing else. And that is what happens in a scan chain also in digital domain. I don't know if you know what is scan chain. No, okay. So, so now, if you cleverly set up a system of equations in this thing, it comes out like a linear algebra. It comes out in a very nice, elegant matrix. And if you invert this matrix, you get all the unknowns. And these are what you are seeing. These are the bits that get into your computer. So you can solve it, okay? And you can tell, okay, you know what, inside that system, if say this is made of, so let's say this is made of resistors, right? Just like I found out what is the value of the resistor, I can exactly tell, okay, by doing this manipulation, I can tell you exactly this is the value of the resistor or capacitor inside the system, okay? So this is one way of a linear algebra. Now, another thing that we have done is, I would like to say, like, without getting into the details of what it is, there is something in an ADC, there is something called a signal to noise ratio, okay? Now, and there is something called a spurious free dynamic range, SFDR, okay? The spurious free dynamic range is, what is the power of the, if I have a sine wave, let's say 1 kilohertz, 2 kilohertz is what? The second harmonic of the sine wave. 3 kilohertz is the third harmonic of the sine wave. So the spurious free dynamic range means any other harmonic of the fundament main signal, the ratio of the two powers is called the SFDR, the maximum power that comes from the fundamental to this thing, spurious. Now, in order to get the clean ADC, means that there should not be any spurs. These harmonic powers are called the spurs. Okay, these are spurious signals. We do not want those. So how do we estimate that? In order to estimate that, we use something called dithering, and that is where I want to now introduce something called. Noise is bad for everybody, right? But noise can be beautiful also. So I'll give you a simple example how noise is beautiful. Okay. So let us say I have a 1-bit ADC. Okay. Let us say we have a 1-bit ADC. Okay. And I need to, the ADC gives you signal. The input to the ADC goes from 0 volts to 1 volt. This is the full scale of the ADC. That means the input to the ADC can go from 0 volt to 1 volt. Okay, and it has only one comparator, and the threshold of the comparator is, let's say, 0.5 volts. So let's call it the threshold of the comparator is 0.5 volts. Now I want to find out what is the value. Can I digitize it to 0.1 volts? Can I get, if I apply 0.1 volts, what will be the output of the ADC? The ADC is just one comparator which has 0.5 volts as the threshold, and the other input is the Vin. Okay, this is the input and 0.5 volts. What will I get? 0. Okay, so this will give me 0. I'm not getting 0.1. Okay, now let us say I keep adding some noise to it. Okay, so I'll add a certain pattern of noise at this point to illustrate that I can really get 0.1 volt. With this comparator output will give me 0 or 1, right? 0 or 1. So now we'll add noise in a certain manner. This is a different kind of noise, but we'll add noise in a certain manner that I will exactly get this 0.1 volts. So let's do this exercise. Suppose to this input Vin, I start adding signals equal to minus 0.5, minus 0.4, minus 0.3, (0.2). Suppose I add this. Okay. So first cycle, I'll add minus 0.5 to 0.1. What will I get? Minus 0.4. And this will give me 0. right? So when in the first cycle, I'll get 0 output. Okay. Next cycle, what will I get? Minus 0.3. It will also give me 0, right? Third cycle, minus 0.2. It will give me 0. Then minus 0.1, 0. This will give me 0. This will give me 0.2, which is 0. This will give me 0. This will give me 0. This will give me, this is exactly at 0.5. Let us say we are lucky, it still gives me 0. Let us say, let's take that as a, we take it 0. Okay. Then I add 0.5. What do I get? I get 1. I take these numbers and average it out. What do I get? 0.1, right? Right? So 10 of these are there. So 1 divided by 10, I get 0.1. So 1 bit comparator, I could get 0.1 exactly, right? Now this is a special kind of thing that I did. Okay. Now I can add, this is a known sequence that I added to the thing. Okay. So this is deterministic. I can add random noise to it and I get this, I can get this performance. So if I add noise to any signal, it can help me give me better and better resolution if I can add it in a clever fashion. And adding noise to a signal in a clever fashion is something called dithering. Okay. And that dithering can give us huge enhancement in the resolution that we get. Okay. So this is a very simple example. This kind of dithering is called deterministic self-subtractive dither. Deterministic because I know exactly what I'm adding. Okay. Self-subtractive because if I average all of them, it is 0. It is automatically subtract. I don't have to do anything special at the output to do a subtraction. This is deterministic self-subtractive dither. And dither is a very common technique used in almost all systems. So when a CD player is playing your music, inside there is a special circuit that adds dither to it, adds noise to it, and it enhances your performance. It quantizes. And in a CD player, it further needs that because this dither actually breaks a periodicity of something called a quantization noise. Quantization noise is periodic. Although it is called noise, it is periodic. So I didn't have the time to get into the math of it, but it is periodic. The dither actually breaks the periodicity of the quantization noise. Now, this dither, I can add, this is a deterministic self-subtractive. I can get a white dither. What is the meaning of white dither? White dither means a signal which has a dither signal. If I take this number and I take the spectrum of this, I should get a flat spectrum. Means all the noise. White light has all colors. White noise has all frequencies. So if I can add a white dither, so now the kind of dither that I add is up in my control. I can add random dither, white dither, low pass dither, high pass dither, any kind of dither that I want. But I should know what I am adding, and my signal processing should take care of this. Okay. So adding dithering and then averaging. Of course, once I have added dither, I have to filter out the dither. This is filtering. Averaging is filtering. So averaging is a low pass filter. Okay. If I average it after some time, it is a low pass filter. So this simply filters it out. And from a 1-bit comparator, I'm getting almost 1/10 resolution, 0.1. I can now, ideally, it will only give me zeros or ones, but I can get 0.1. If I add finer resolution dither, I can get 0.01 kind of steps in the ADC. So this. No.
You already have the 0.1 volt resolution voltage with you, right? Just giving you comparators.
Right. No. No, actually, this is just an illustration. So the way the dither is added is, the way this voltage is added is not like this actually. You use capacitors and switch their capacitor to a certain voltage. This is just an example on the board to give you this.
Right, but the capacitor also will be in the same resolution as what you
need not be. That is the beauty of it. If it is not in the same resolution, you will get better accuracy. In the deterministic case, almost you get the same accuracy. Because, okay, I would say yes in the real implementation. Why yes? Because in a deterministic case, you add this dither in differential mode. When you're adding in differential mode, if I want to add minus 0.5, I'll put the capacitor in this manner. If I want to add plus 0.5, I'll put it in this manner. So the steps will be perfectly this, and this steps will be equal. They might not be exactly 0.1, but they will be not off. So they'll cancel out each other. So the average of this will always be 0. As long as I have this average equal to 0, it should be non-subtractive. And in a differential implementation, it always comes out to be 0. Every clock cycle you do it. So you trade off accuracy, speed versus the accuracy. So this is what this was seen in the 1962. So what they did is, in those days, they had 1-bit signal, PCM, pulse coded modulation. So noise was considered as the ugliest until dither was invented. People started seeing the beauty in it. So it is really amazing what noise can do. And modern day data converters, you will see they do add all different kinds of noise to enhance the performance. So they used it for picture coding. So this is the original image, 6-bit image. It took a lot of bandwidth to transmit in those days, right? A lot of time. Now what they did is, you know what, they cannot transmit 6-bit. They converted that to 2-bit. Okay. If they transmit the 2-bit image straight, you will get this quality. See how the face has been distorted. Now they added dither, pseudo-random dither to it. Keep in mind, it is not a full dither. What is the difference between random and pseudo-random? Random dither is fully random, what nature gives you. Pseudo-random has a certain amount of periodicity, and the periodicity should be out not within our vision, within our sight. For example, if I'm trying to receive a HD image, okay, from one frame to another, so the periodicity of the pseudo-random sequence should be at least 100 frames out. So that, if it repeats after 100 frames, it's okay. Because after 100 frames, it's totally a new image anyway, because it goes 27 frames per second in the for our eyes to not see a motion picture. So four images, 4 things gone by. So so this is a pseudo-random sequence that was added. So they transmitted 2-bit sequence with a pseudo-random noise added, and you saw that this quality and this quality is almost the same. Okay, and exactly the same dither was used here to get back this accuracy. So the dither gave you back the accuracy with a 2-bit image and accuracy close to a 6-bit image. Okay, and we exploited that dither to improve the accuracy of our to estimate the values of the R's and C's in our system. Okay, so okay, so let me not get into this. Now, how do you add this dither? So what happens is that it's a very small, simple digital circuit. Bunch of shift registers, few XOR gates, okay, and you get these bits out of this. Okay, now this bunch of XOR gates and the shift register gives you the pseudo-random sequence with a certain periodicity that you have to figure out, and that is already tabulated. Okay, it's tabulated, well tabulated in error control coding books. It's already given. If you look into, I'm sure you have an error control coding course or something, source coding, channel coding, undergraduate level. So in that they'll have Galois field polynomials and all. In that they will tell you exactly what is the periodicity of any pseudo-random sequence. Now this pseudo-random sequence goes and controls this bank of capacitors. Okay, this is a single-ended implementation. If you have a differential, you will have this and you swap them and you get a random dither or you get a deterministic dither that way. Okay, so this is the chip layout that we had done. We had built a 12-bit ADC and we got SFDR, the very good clean performance out of this. This is the 5-stage pipeline ADC that was done, and this is the overall SNR plot that we got. Now, this is another mixed signal SOC that we did for battery management in electric cars. So in an electric car, we had to make sure that the batteries are a bunch of cells, right? And all the cells should charge uniformly and should charge at the same rate. If there is any discrepancy in the charging rate of the two cells, then there will be short circuit current which will degrade the battery life. Okay. So you need and this was for, actually this is in production right now by AMS, Austria Microsystems. They actually taped out, they supported. This is used in BMW cars at this point in Europe. This thing. So this we needed a signal conditioning circuit, which is a programmable gain amplifier. And what this circuit did was it was sensing the current flowing into the battery. And we had to sense very small amount of current. So we needed an amplifier, programmable gain amplifier, and we needed a 16-bit ADC. And the 16-bit ADC was realized using the PGA was realized using a bank of op amps and capacitors. And the 16-bit ADC was realized using a delta sigma architecture, okay, with feedback. And this was a full chip that we tested. It was in 0.35 micron process in AMS Austria Microsystems process. These Austria Microsystems are very good in very precision circuits. So precision means anything above 14 bits is precision. Okay, anything above 100 megahertz is high speed in ADCs. Okay, so that is the norm that is followed in the industry. I will skip this at this point because this is now just to give you a few things I want to share about ADCs and DACs. Just as I thought it's good to give a 5-minute about career prospect if it is okay. So that kind of. So in India there is a great demand for a data converter people. Okay. There is only what made me proud when I went to US last summer was this. I went there was this conference, Midwest conference, so I went to Dallas. So I met my friend in TI. So what he told me, I got goosebumps. He said, TI Bangalore team, they dictate what needs to be done in TI US in terms of ADCs. Okay, TI Bangalore, they will TI Dallas headquarters. TI's headquarters tells them, can you do this? Said, we are not going to do this. We'll do this, and they do it. So TI Texas Instruments Bangalore has a top-notch high-speed ADCs, and they have really built gigasample per second, and they've given analog devices a run for their money. Okay, and to give you a perspective, in 2007, there was this 3.6 gigasample per second, 12-bit ADC. Can you guess the cost of that? It is this size of a chip, this by this. Can you guess the cost of it? In 2007, $3,000 one ADC. $3,000 one ADC. Okay, and imagine, you know, in a base station, how many ADCs go in? Hundreds of ADCs. Now imagine how many base stations are in Bhubaneswar. Imagine the amount of money that these people would have spent to set up the base stations, and how much money TI would have made at that time. Now, to give you another perspective, 2012, analog devices came up with a counterpart. Now, guess what is the cost of that ADC? Go to the market, it is $400. So, if you can build an ADC in India of that specification, you will be very much valued. Okay, ADCs, and another thing is the DACs. DACs at that time, the same DAC, 3.6 GSPS DAC was roughly $800. And to give you another, the reason I focus mostly on ADCs is because ADCs are much more challenging than DACs. Okay, DACs are a little easier to build, and the price reflects that. Okay, so now in India there is a lot of dearth of data converter designers. TI is the only one which has been able to successfully do quite a bit of ADCs. Cosmic Circuits was one of them, which did some ADCs, but not very high frequency ADCs. So the thing is that in India, we have access to the technology, but we don't have access to the manpower. So if you are a good analog designer, okay, and especially if you are a high speed analog designer, you will be valued a lot. The other company which is doing a lot of high-speed ADC and DAC design is MaxLinear in Bangalore also. They are also developing. One of my friend, colleague, he is at MaxLinear. He is leading that effort. So just to, this thing, so ADC DAC, there is a huge demand. And China, for example, cannot procure these ADCs directly from the US. It has to go via Italy. It takes it there. China requires these ADCs. So a lot of the people in India who are working on ADCs and DACs actually get funded from, that's what is happening. So if you want to pursue a career in analog design, I think you should pursue, I'm not saying that, see, ADC DAC is one block. The RF is another different block, so right? RF receiver and transceivers they are a different ball game, okay? To give you a perspective, analog design is an art. RF design is called black magic. And it truly is still a black magic analog design. And analog design is an art. And yesterday I saw one of your students had done the painting, right? That pencil sketch of yours. Okay. Okay. So if you are good, so you can become a good analog designer. You need to see, and a good analog designer will see a symmetry in everything. We human beings are almost symmetric around the center part, right? Almost all analog. ST micro. Okay. So you can see the amount of symmetry that goes into making an analog circuit. You can see that they are nicely half up. See, there is a mirror. Every layout it will be exactly mirror images. So they look very symmetric, power delivery and everything. So I think you are already getting trained in layout and everything, taping out chips from here.
Yeah, there is a group that
Group, right?
plan to start integrating that in the course as well.
Right.
We have courses that we do there, but very simple. But we are trying to do open source in a complicated.
I see.
And all that and
Okay. So there is all I want to say is that there is a dearth of analog engineers in India. There is a huge dearth of analog engineers in India. And there is a need for people to get trained. And there is a lot of scope for analog mixed signal design. And if you can design good ADCs, your demand will be just great. So I think, I don't know, I hope I did a small little bit of justice to the talk. So thank you for your time. Any questions?
Actually, continuing on that carrier side, maybe you can give a little perspective on if some of the students are interested in this carrier side, like becoming ADC designers, what